In this part 2 of our 5-part series on Peek at All Those Pills, Psychopharmacology 001, we'll be looking at mechanism of action. Once a client has swallowed that pill, what happens to it? How does it get into their bloodstream, and how does it have its effect, and how is it biodegraded? If you are looking at this in the PowerPoint slideshow presentation format, there are 3 slides connected to this idea of the molecular targets of our psychotropic drugs. How do our drugs work? One of the ways is that they block in the transporter that takes the neurotransmitter from the synapse back up into the axon. So that is the 12-membrane region transporter, and about 30% of our medications work on this. Anything that says it is a reuptake transporter inhibitor, that's what these drugs are. Then another way that many of our medications work is through the 7-transmembrane region of the G protein linked molecules, and those are over 30% of our psychotropic drugs. These are the metabotropic, the slower acting. When I said slower acting, I didn't mean that they are like extended release medications. Rather, the G protein coupled, as we've seen in other portions of these lectures, the G protein coupled must first have an enzymatic reaction right after the molecule of the neurotransmitter binds, and then there are further downstream. Now, another way, the 5th of our 5 molecular targets is number 3 are enzymes, and these break down the neurotransmitter. So we have enzymes that break down like acetylcholine esterase. Then we have 4 transmembrane region ligand-gated ion channels for about 20% of our medications. That little tom-tom drum there in the center of the slide, that is a GABA type receptor. It is also a glutamate type receptor. So both glutamate and GABA are 4 transmembrane region. And when it says ligand, it just means that the molecule of either glutamate or GABA must be binding to that site. And then up in the upper right-hand corner is looks like a cone, and those are 6 transmembrane region voltage-gated ion channels through which about 10% of our medications work. These would be our medications for primarily bipolar disorder, and they work primarily on sodium and calcium channels. Here's another way to look at mode of action. Now we're going to be looking at many of our drugs work by only one mode of action, whether they are a serotonin transport reuptake inhibitor or whether they are inhibiting action at a 4 transmembrane region receptor, or whether they are working at the conical 6 transmembrane ion channel receptors, or whether they are enzymatic biodegrading enzymes. So we have there at the bottom, or I'm sorry, in the middle column there, middle row, we have the pharmacological name of a transport reuptake inhibitor would be an SSRI, because it's only working on the serotonin. For inhibition in the 4 transmembrane region, those would be medications that work for anxiety, for sleep, and their pharmacological name is GABA-A PAM, which stands for a positive allosteric modulator. We will be covering that in topic 7 of our course coming up. And then the conical inhibitors of ion channels, those are primarily our anticonvulsants, also known as antimanic, and some of them are also anti-nociceptive, which means just they are pain-controlling medications such as pregabalin or Lyrica, and their pharmacological name is VGSC, voltage-gated sodium channel, and there's also voltage-gated calcium channels. And then finally inhibition, the enzymes that break down things, and the primary one that we'll be looking at is MAOI, monoamine oxidase inhibitor. And finally, down at the bottom, we have an antipsychotic, which is a second generation reuptake inhibitor, SGRI. And we'll be looking at those a lot in 635 in our third class. Now, many of our medications, as we've just said, work in only one way, but we have a number of medications now that are multifunctional, and that means that they, like in the inhibition of the reuptake transporter, not just serotonin, but also norepinephrine or also dopamine are inhibited, and those are our antidepressants. That also work as anxiolytics and as pain medications. And so a pharmacological name for that would be a selective norepinephrine reuptake inhibitor. Now, these medications, while they work that way, there are also medications that work on that G-coupled protein, and they can be both antagonists, as you see there at the bottom on the far right. They can be antagonists, they can be partial agonists, they can be antagonists. It depends upon which receptor, which site, which location in the brain. It's beginning to get complicated, and we will get into that when we are talking about the psychotic spectrum in 635 class 3. Aren't you going to look forward to some stuff coming up? Another multimodal agent that works both by inhibiting the reuptake of serotonin in the serotonin reuptake transporter is, and also working on the G-coupled protein as a partial agonist, is the newer medication Vibrid or vilazodone, which is a serotonin partial agonist reuptake inhibitor, Aspari. Is it important to remember all of these things and know all these names? Yes and no. I think we need to have a really good understanding of the mechanisms of how these medications work, even though we may not be giving this type of detailed information to clients. We as professionals need to know which medication we're giving and how it works, because we might want to have something that works on dual fronts rather than just a single action medication. So we have medications that work on a single function, like a simple serotonin reuptake inhibitor. We have medications that work in several functions, such as the serotonin norepinephrine reuptake inhibitors. Now we have also medications that are multimodal. They work on several different actions at once. They are inhibiting the reuptake of medications through the transport system. They are acting on the G-coupled protein system, either as antagonists or agonists, and they are working on the GABA glutamate systems through serotonin as an antagonist, a serotonin 3 receptor, working on acetylcholine and norepinephrine. These multimodal new agents are the ones bivioxetine and carpriprazine. Have you asked yourself what it is that powers those little trolleys, the transporters that take the molecule of the neurotransmitter from the synapse back up into the axon? Well, their gasoline is adenosinotriphosphatase. It is the sodium pump, and this sodium pump is pumping sodium out of the cell in order to create a downhill gradient that as the sodium is coming out, then the transporter is able to go up the hill and into the axon. That's enough of that. Those transporter pumps will get the neurotransmitter into the axon, but they are just the first part of the journey. Then that neurotransmitter needs also to get back into a vesicular sac so that eventually it can travel back down to the synapse area and be released back into the synaptic space. So the serotonin transporter pump by adenosine triphosphatase is then complemented by another pump, the proton pump, that takes the neurotransmitter in the axon and puts it back into the vesicular sac. And there are quite a few of those, as you see there at the bottom. You don't need to memorize all of that, but just to know that there is a vesicular monoamine transporter for serotonin, norepinephrine, dopamine, and histamine. There is an inhibitory transporter for GABA, and then there's the acetylcholine, so each of them has their own transporter into the vesicular sac. Another concept that is very important for our work is how enzymes work. Enzymes bind to, or a substrate binds to the enzyme, or vice versa, an enzyme to the substrate that then breaks down the substrate. We'll begin to look at that in the next few slides. I've kept these slides in this shorter presentation just because they are in STAL, found in Chapter 2. The enzymes, there are two different forms. Some are irreversible inhibitors that once they bind, that's it. That receptor is out of luck, or not the receptor, the enzyme has bound and cannot be removed. Other of these enzymes are able to be removed, reversible inhibitors. So when they substrate binds to them, the inhibitor can be removed. One of the examples of an irreversible would be the mustard gas that was used in biochemical warfare. We talked about the different mechanisms, both single function, multifunction, and multimodal of many of our medications. However, we have an especially important medication called lithium and some of the other mood stabilizers that they also work on what's called the glycogen synthase kinase, or GSK3. And you can see here in the graphic that it is a multi-signal transduction cascade going down, where it blocks this enzyme that is needed for further action in the cell. Lithium works this way, possibly Depakote might work that way, and as people have investigated electroconvulsive therapy, it might also have an impact upon the GSK3. The end result of this is that it could lead to further neuroprotective actions and long-term plasticity of the nervous system, therefore contributing to mood stabilizing actions. Another concept that enters greatly into our work is the cytochrome P450 system, or they're just called CYP 450 for short. They are classified in different ways. We see 5 pretty colored little, kind of look like stars or maybe ghost figures, I don't know, stretching across this slide. And they have numbers and letters and numbers. So the P450 system, all of the enzymes in this system are identified first by a letter, which is the family to which they belong, and then by subtype, which is the letter designation, and then by a gene product, which is the second number there. We have, primarily in mental health and psychiatry, we have 5 that enter into our work: the 1A2, 2D6, 2C9, 2C19, and 3A4. Now, these enzymes and the medications we give interact, and if an enzyme acts too quickly, it is an inducer of the medication, and the body processes it too quickly, and so there may be actually a lower level of serum level of the medication we're administering. Or in other cases, the enzyme is an inhibitor of the medication we're giving, and so it doesn't break down, and therefore the medication serum levels are going to build up. So we have to be careful of this, and there are charts, and we'll have a few in another 2 slides. We have that tell us whether a medication is an inducer, making it process too quickly, or an inhibitor, making it process slowly and possibly building up. This whole concept gets even more complicated because our medications are substrates of these enzymes, but then some of our medications actually work with these enzymes on other substrates, and that's what this slide shows. Medication that is in the class of antidepressants, fluvoxamine, which we don't use that much in this country, works with the enzyme 1A2. But when it works with the enzyme 1A2 and binds to it, it slows down the activity of that enzyme. It inhibits it. And so other medications which are substrates that should be worked on by that enzyme, such as our antidepressant duloxetine, such as an antipsychotic clozapine and olanzapine and zodapine, such as many of the tricyclic antidepressants that we'll be looking at, their serum levels could then build up because fluoxetine is being administered concurrently with any of those. So you see in the graphic that in the gut, the medication is coming in, and then you see the little round circle of the F that has kind of sat on the shoulder of that little enzyme, and therefore the red line through it says it's being slowed down. And if you see then on the other side in the bloodstream, the medication is building up, it is accumulating, serum level is rising. Another important interaction between our medications and not only other medications and their enzymes, but our medications and external habits such as smoking can affect, along with the enzyme, can affect the level of medications in the blood. The most famous one that you may already be familiar with is that cigarette smoking is an inducer of the 1A2 enzyme, which metabolizes two of our medications, or three, olanzapine, clozapine, and zodapine, causing there to be lower doses of the medication in the bloodstream. So we have people in the hospital, and we do not have smoking in the hospital. We start them on a medication such as olanzapine, Zyprexa. Then they're discharged, and they go back to their habit of smoking. Now, they were stabilized in the hospital at 1 dose of olanzapine, but now they get home and all of a sudden their symptoms are beginning to break through and people are wondering what's happened. Well, the smoking has induced the enzyme, which has sped up the level of the biodegradation or elimination of the olanzapine. Therefore, the person may need a higher dose of olanzapine if they continue to smoke. At the top of this slide, you see the fancy word hydroxylation. That is part of the process of what an enzyme does as it works on a substrate of medication to break it down. Now, on the far right side, you see some inhibitors. Those are the medications, paroxetine, fluoxetine, etc., that can bind to the enzyme. And when these bind to the enzyme, especially the 2D6, they slow down the action of the enzyme, so it does not work as well on some of the substrates which are there in the left-hand column. This is why some of our medications can slow down the action of other medications. Now, you'll notice here 2D6, some of the substrates are many of the medications that we use in our regular practice: atomoxetine or Strattera, venlafaxine or Effexor, duloxetine or Cymbalta, paroxetine or Paxil, risperidone or Risperdal, clozapine or Clozaril, olanzapine or Zyprexa, aripiprazole or Abilify, and iloperidone or oh gosh, I forgot the generic for that right now. But all of those are bind to the 2D6 enzyme. So the 2D6 enzyme is the one that is most involved in, or the majority, involved in the majority of our psychotropic medications. All of this stuff about the inhibiting and the inducing, whether it's a substrate or whether it is the enzyme or it is an acting upon the enzyme, All of these can be found in other charts. Over time, you will start to know some of this by heart, but it is not something that you need to sit and be memorizing right now. Another enzyme that acts upon a lot of our different psychotropic medications is the 3A4 enzyme. And on the left-hand side, you see the substrates, the medications upon which the enzyme acts. Now, that enzyme, if it is slowed down or inhibited by some of the medications on the right, will then not process the medications on the left well, and the serum levels of those medications can increase in the bloodstream. So I'm hoping this is becoming a little clearer at this point, that if something is induced, that means its metabolism is speeded up, with the result that there is less of a serum level of the medication. If something is inhibited, that means that the action of the enzyme is slowed down, and so the presence serum level of the medication can increase. This is the last slide in this second portion of our 5 portions on peek at psychopharmacology. In here we see the 3A4 enzyme, and we see some of its inducers. The one I want you to notice the most is carbamazepine. Carbamazepine is an anticonvulsant. It is a mood stabilizer, but it is a medication that you need to be really careful if someone is on carbamazepine to watch whatever other medications they are on or which medications you're going to prescribe, because carbamazepine is quite involved. It can induce some medications, it can inhibit other medications, and it even inhibits its own self. So it's not a medication that I use as a first-line choice at all. All right, this has been our quick overview of how the medications work on the transporter systems, on the enzyme systems, on the ion systems of channel, calcium and sodium, and on the ligand gated of glutamate and GABA. We've also then looked at this important concept of binding power and agonist-antagonist, and now we have looked at the enzyme impact on our medications through the CYP450 system.